Now we are going to learn how to solve wave equation. So wave equation is one of the PDE, partial differential equation. So now we can try example 9.10. Sorry. So 9.10 is actually similar to the previous lecture, which is we just want to prove that this equation is related to the wave equation. So actually this is not the way how to solve the wave equation, but we can just recall this, how to prove that this equation is related to wave equation. So actually u equal to this function. This itself is the solution of the wave equation. Okay, so when we have this solution and we want to prove it is related to wave equation, we just need to find the first derivative with respect to x, second derivative with respect to x, first derivative with respect to t, second derivative with respect to t, and then after we found the uxx and utt, we compare them. So we found that this is the relation between the two component, and it is satisfies the wave equation. Okay, and we want to see what is the behavior of this equation. We can plot this equation for various value of x and 3 values of ct. So ct we make it -1, 0 and 1. Okay, and we want to see the value of u obtained from the calculation of x and ct. So this is the diagram, the sketch of the curve for different value of ct. And if you look at here, when time is increasing, the wave is propagating from right to left. Okay, from right to left, from yellow, red and green. So this is the behavior of this equation, and this is the application of the wave equation, one of the application, to see the propagation of the wave. Alright, so now we go to the next example. Now we will understand how to solve the wave equation. So which equation we are going to solve? Actually we are going to solve the wave equation itself. So this is the formula of wave equation. So again, when we want to solve PDE, we need to have many boundary conditions to in order to solve the wave equation. Okay, the PDE equation itself. Okay, so in this example we have 2 conditions or boundary conditions. So the first one is when time is 0, the velocity is 0 for all x. Okay, for all displacement, for all location or position, the time of the wave, the speed of the wave is 0 at time 0. Okay, and the second boundary condition is the initial displacement, where at time 0 again, when x is between 0 and 1, the value of the value of u is equal to 1 minus x. So when x is between -1 and 0, the value of u is 1 plus x. And otherwise, if the value of x is other than this range, the value of u is 0. Okay, So hopefully you understand the conditions. Now we are going to solve it. Again, we need to use the formula given in the previous note. This is the solution of wave equation formula. So hopefully you use the right formula to solve the wave equation. So as you can see, we have the C component right here. So this C is related to this C again. Okay, and we use this formula. So how to relate this formula with the conditions? Now, in PDE solutions, we just put the formula, and then we just, after that, we quickly consider the boundary conditions. So we consider the first boundary condition, where the initial speed is 0 for any value of x. Okay. And now we just need to differentiate this with respect to t to get the velocity. Okay. So this is the vertical velocity. If you look in the diagram, and then when we differentiate this, we can see that the CT component is differentiated to eliminate this the t, and the c is we can take the c outside like this. Okay, and f prime and g prime is the is df dt. Okay, and g is dg dt. Okay, so and this all is equal to 0 for all x. Alright, so now when we consider this equation, we can eliminate c. Why? Because it is equal to 0. And then we have this formula. We can have this equation, sorry. And then we do integration. When we do integration, we will have additional constant k. Okay, and we have the f and g function back. Okay, and then we can arrange so that g is in term of f and k right here. Okay, and now after we get the function of g, we substitute the this equation back to the original equation right here. Okay, but again, since when we go back to the original equation, we are no longer considering the boundary condition. Therefore, we have the x minus ct back. We don't only consider x, but we have x minus ct back. So if you look at this equation, okay, we have f function with respect to x plus ct, and g is replaced with this function f with respect to x minus ct minus ct, because g is the function respect to x minus ct. Okay, and we have minus k. So this is the solution that we have so far, but we need to consider another boundary condition to have the complete solution. Okay, just follow this cursor so that you understand where I'm pointing right now. So when we consider the second boundary condition, when time is 0, which is the initial, we consider the initial displacement. When time is 0, the u is equal to the big F function, where the big F function is this one. Okay. So we replace u with big F. Okay, right here we replace with big F, and then since t is 0 again, so we just eliminate the ct since t is 0, so we don't consider the c. So what left is x, so fx plus fx minus k. This is from this function, and then we just add them, because since there's no different, this is plus, this is minus, but when t is 0, this is similar, so we can add them. So 2fx, 2f minus k. Okay. So when we consider this equation, left side, right side and left side, we can make the small f function as the subject, and we can rearrange so that f is in terms of these components. So we put the big F to the right hand side. So these are the function of the small f. Okay, and then so this is the solution that we want to find, and we can substitute this function back to the previous solution that we have, which is this one. So we replace the small f with this function, which includes the big F. Okay, so when we substitute, these are the function that we get. If you look at here, we have k component right here. Okay, and in this function we don't have any k. Why? Because when we put back this function here, we have k over 2, and another component we have k over 2 again, and we have minus k right here. So the k over 2 plus k over 2 is equal to k minus k, then k is eliminated. Okay, so this is the final solution of the PDE of the wave equation given in this example. So if you want to understand what is this function looks like, so this is the diagram. So the first diagram is when time is equal to 0. So this is the initial condition. So the wave is the amplitude is at its maximum at 0 position. So this is position, not time. At 0 position, the amplitude is maximum, and when time progresses, you can the wave is split, and half of the wave go to the right hand side, and half of them go to the left hand side. So it's like an explosion, or when you pull a string and then you release it, the wave is split into two direction, two end of the string. Okay, so this is the application of this equation. It doesn't have to be a string. It can be a table or a bar or anything that we can think which is related to this phenomena or this behavior. Okay,